By the time engineers finish designing a part, they know quite a bit about it. What it will look like, what it's supposed to do, the environment it'll be used in, and probably how the part will be made. Often, the toughest task is figuring out what it should be made of. And when engineers are thinking of thermoplastics, the number of choices can be overwhelming. There are more than 2,000 materials available, but only a few, or maybe one, is the right one. Naturally, the choice rests on the qualities needed for that particular application. An engineer, for example, may need a stiff material or a flexible one, a hard plastic or a rather soft one, or a material that can resist certain chemicals, withstand heat, electricity, wind, rain, or sunlight. And a molder may need a material that can be molded in a certain way or at certain temperatures. To put numbers on these properties, testing engineers have devised a variety of standard ASTM laboratory tests that show how a given thermoplastic performs under specific conditions. The results of these tests allow us to gauge how a material might perform in the finished part, and they provide a way to compare one material against another. The properties engineers evaluate most often are mechanical properties, a material's strength, toughness, flexibility, or hardness; thermal properties, how it behaves under heat or cold or when exposed to flame; and electrical properties, does it conduct electricity or not, and how much and under what conditions. When measuring these properties with tests, it is critical to decide precisely what characteristics we're interested in. Take the question of strength, for example. There are actually many sides to that question. One measure of strength is a test of tensile properties performed in an apparatus like this. We place a sample of the material between two jaws. Then, at a fixed rate of speed, one jaw begins moving away from the other, exerting a tensile stress on the sample. The device attached to the sample measures how much the material elongates. Eventually, the sample breaks, and we can record the amount of force required to break it. That number is the tensile strength, given in pounds per square inch. The higher the number, the stronger the material. But it's only a basic measure of strength because there's much more at work here. If we plot the amount of stress we applied against the elongation of the sample, we produce what is called a stress-strain curve. As the jaws of the apparatus move apart, the stress and strain on the material increase until the sample breaks. This second material, for example, has a similar break point, but it clearly elongated much more before breaking. And under the same stress, this third plastic elongated very little. So the final elongation, expressed as a percent, adds another dimension to the strength picture. We can also consider the ratio of stress to strain, called the tensile modulus, which is essentially a measure of stiffness. The higher the tensile modulus, the less the material will elongate under a given stress. But this value is usually only measured here in the linear portion of the curve. Ideally, the stress expected on the finished part should fall in this region. Now here's how these three values, tensile strength, final elongation, and tensile modulus, could come into play in selecting a material. You might think of tensile strength as the first cut. Any material that cannot withstand the design stress can be immediately ruled out. Next, you might consider the final elongation values. A material that will withstand the force, but stretch unacceptably, might also be ruled out. But don't necessarily look for extremely low elongation either, especially if the part would be subject to sudden stress or impact. More about that in a moment. From here, you might consider the tensile modulus. The greater the modulus, the stiffer the material. But that still doesn't completely answer the strength question. Many materials might have the same tensile modulus, yet behave quite differently under a different type of force. For example, what would happen if you tried to bend the materials? The flexural modulus test answers that question. It can be performed manually or on automated equipment like this. The sample is suspended between 2 points and a load is applied exactly in the middle. We then record how much force the sample withstands before breaking. That's the flexural modulus, expressed in pounds per square inch. The higher the number, the stiffer the material. Nylon, for example, tests at 200,000 psi, moderately stiff. Celcon polyacetal is much stiffer, with a flex modulus of about 350,000 psi. For comparison, this piece of aluminum comes in at about 10 million psi. This sample of Rightflex thermoplastic elastomer doesn't break at all. To get meaningful information, we have to record the force it takes to produce a set deflection or strain, usually 5% compression or extension at the surface of the material. It is entirely possible that two materials with the same tensile strength as measured before could have somewhat different flexural properties. That's because the flexural modulus actually describes the interplay between the tensile forces at the lower surface of the sample and the compressive forces on the upper surface. While the flex modulus generally follows tensile modulus, it doesn't always. So if a finished part would be subject to bending or flexing force, the flexural modulus might be a somewhat finer measure of its ultimate suitability. Or would it? Neither of these values considers rapid or sudden stress, a different question entirely. To find out what happens when we strike the plastic, we run an IZOD impact test. Here we prepare a sample of the material in a standard shape known as a notched IZOD. We fix the sample here and raise the pendulum to a set height. The pendulum will then fall, strike the plastic, and come up the other side of the dial. By measuring the difference between the starting and ending heights of the pendulum, we calculate how much force was consumed in breaking the sample. That's the IZOD impact resistance, measured in foot-pounds per inch of sample. The higher the number, the more force it absorbs during impact. Materials with the high IZOD impact values are considered tough, meaning they stand up to sudden stresses better than materials with low IZOD impact values. In general, flexible materials have higher IZOD values, chiefly because they absorb some of the force before breaking. Some very tough materials don't break in the test, so they must be tested at low temperatures to yield meaningful information. Compared to the other mechanical test values, the IZOD impact resistance generally mirrors elongation more closely than any other. But still, there can be significant differences between materials. You may have to consider all these values when considering strength, taking into account the amount, the direction, and the speed of the force the finished part must withstand. Yet none of these mechanical tests consider the environment the part must endure. For that, we can apply a number of thermal tests. To compare how different materials hold their shape under heat, we use the heat deflection test. A standard sample is suspended between two supports 4 inches apart. We then place a predetermined stress on the material, either 66 or 264 psi, and place the whole assembly into an oil bath. We then raise the temperature of the bath at a rate of 2 degrees centigrade per minute. At some point, the material usually begins to soften and deflect under the stress. When the sample deflects 10/1000ths of an inch, we record the temperature, which is known as the heat deflection temperature, or HDT. It's a standardized measure of the amount of temperature a material can withstand before it begins to lose stiffness. So the HDT is best used to compare the relative heat resistance of materials, rather than to establish the upper temperature limit for a given thermoplastic. In general, the HDT of a material depends on the chemical nature of its monomers, its polymer architecture, fillers, and other molecular factors. There is usually no correlation between HDT and its room temperature mechanical properties. In some applications, it may be necessary to know how a material behaves when a flame is applied. Some materials will simply melt, while others will burn to one degree or another. The flammability rating depends on the rate at which the material burns. Different materials will burn for varying periods of time, while others do not support burning at all. Tests like these are only preliminary indicators of flammability. The shape and size of the finished part can affect its burning behavior significantly. A thermal property of interest to molders is the melt index, which is a basic measure of the material's melt viscosity. A material sample goes into this preheated cylinder and is placed under weighted pressure by a preheated piston. The pressure and temperature vary with the material being tested. As the material begins to protrude through the opening below, it's cut off flush at 5 minutes and again at 6 minutes. The material is then allowed to flow again, and at a set time, the material is cut off a final time and weighed, yielding the melt index, given in grams extruded per 10 minutes. The more viscous the material, the lower the melt index. Less material flows from the apparatus at a given time, temperature, and pressure. In general, these are filled polymers or the highly branched polymers with high molecular weights. The melt index doesn't indicate much about the material's behavior in the finished part, however. It's primarily of interest in processing. The third group of properties considered when selecting materials are the electrical characteristics. In an electrical application, the part might be exposed to electrical arcs, for example. To determine how a material might react to a live arc, we can perform an arc resistance test. We suspend a sample between two contacts, then apply high voltage with increasing amounts of current. At some point, the arc disappears into the material. The level of current at that point determines the arc resistance of the material. It essentially measures how well a material resists forming a conductive path in the presence of an electrical arc. For the most part, arc resistance is a relative measure of the electrical properties of identically shaped samples under identical conditions. The actual value is quite dependent on the shape of the part, the nature of the arc and current, and the distances involved. A more definitive measure of insulation properties is the dielectric strength test. A sample is placed between brass electrodes. Starting with 0 voltage, we increase the voltage at a rate of 500 volts per second until a sudden excessive current flows through the material. The voltage at that point, expressed in kilovolts, is the dielectric strength. The higher the value, the greater the short-term insulating ability of the material. Naturally, the thickness of the material affects this value significantly, and so does humidity, moisture content, and the geometry of the part. In general, the dielectric strength is most useful for comparing identical samples of 2 or more materials. Another electrical test, which measures real-world conditions, is the comparative tracking index. Here we're measuring how well a material can maintain its electrical condition when its surface is contaminated. We place a contaminant, an ammonium chloride solution, on the surface of the sample. We then apply increasing levels of voltage. At some point, the current arcs across the contaminated surface. That voltage level is the comparative tracking index, or CTI. The higher the value, the better the material will resist conducting electricity when contaminated with an electrolyte. While electrical properties often appear in product specifications, the actual values are dependent on the specific conditions used in the test. Where electrical properties are critical to the application, it's best to run side-by-side tests of identical samples of the materials being considered. So, when selecting a material for a particular part, all 3 groups of properties and their specific values may come into play. Often, a sound strategy is to focus on a primary or limiting characteristic for the part to end up with a short list of possible materials. Then consider the secondary properties in turn to narrow the field even further. An example, say we've designed this impeller. In end use, it will be subject to frequent impacts. It will also be subject to some slow loads and some heat, about 150 degrees Fahrenheit. And there are insulated wires nearby. But If the part cannot stand the impact of about 4 foot-pounds per inch of notch, those other conditions are really academic. Clearly, the limiting or primary characteristic is the impact resistance. If it's not sufficiently tough, it's totally useless. So when looking at possible materials, we can automatically rule out any product with an IZOD impact resistance below 4 foot-pounds per inch of notch. The list of possibilities is now more manageable. From here, we might look at the thermal or electrical properties and eliminate any materials that are close to limits or out of range. And the list gets shorter still. Next, we might examine the mechanical properties a little more closely. We can tolerate some elongation at load, but not much, or else the part will deform. So out go the materials with high elongation values. All else being equal, we might now select those with thermal or electrical properties far above our limits, just for a margin of safety. At some point, we'll end up with a short list of materials that simply can't be evaluated further by their standard values. Now, any number of factors could be brought into the game: price, processing ease, colors, surface finish, weight, and others. When left with 2 or 3 seemingly suitable materials, many users find it useful to actually make the part from all of the materials and put them through real-world tests, which can mean anything from dropping them off a building to running them through a car wash. But when such definitive tests aren't practical or are too expensive to conduct on dozens of materials, standard laboratory tests offer a logical starting